Hello, testing 1 2 1 2. JHS open source, can you just send me a quick message via the chat just to say that you can hear me correctly? Even just a hi will be fine. I understand that there's some delay between me actually saying anything and you hearing it, but we'll just have to deal with that. So as you can see, I should have changed the screen to Circuit Wizard now, everybody, and put simply, Circuit Wizard is a simulation program. I use it a lot to simulate my own components and circuitry that I want to build before I actually send them to you, and it just helps me prototype without investing a whole lot of money and time into building this on a breadboard or anything like that. Now let's just do an example, because JHS open source has said what is Kirchhoff's voltage and current laws. Now let's just use a battery here and let's get some resistors. Well, Kirchhoff's voltage law is actually quite simple. It's basically saying that the voltage of a power supply is shared among each of its resistors, and the easiest example of this is literally just 3 resistors in series hooked up to a battery. Now, the easiest way to demonstrate this is through Circuit Wizard or another SPICE program of your choice. As you can see, the current going through this one is 3 milliamps, but that's not important when we're looking at the voltage law. But what we are looking at is at each side of the resistor, it drops by 3 volts. 3 and 0 volts. Sorry about the sound being very quiet, I'm just going to turn it up. There we go. Is that better? I've just turned the mic and the desktop audio up as well. So if you're hearing this then any louder, then please let me know. But I am working on it. So just in case you didn't hear that very well, Kirchhoff's voltage law essentially says that the voltage of a power source is split up between each resistor in series. Now, as you might know from other experiments, is if you have 2 resistors in parallel, then they can be joined together, and by using the parallel resistor formula, you get a value for a single resistor that is smaller than the 2 resistors in parallel. Okay, thank you for joining me, Goose183. Is that... good, okay. Thank you for letting me know. I shall... If it still gets too quiet for you, then please let me know and I'll turn it up, but I have some family members who are trying to sleep right now, so I can't be all that loud, okay? So, let's move on to Kirchhoff's current law this time. As you can see with the voltage, it is different. No, so Kirchhoff's current law is basically saying that, let me get rid of some of these, is basically saying that the amount of current in a circuit has to stay constant throughout it, and despite which path it goes down. So I'm just going to simply make a quick circuit in which there's 1 resistor connected to 2 that are in parallel, and we can measure the current going through it using Circuit Wizard. So as you can see, there is 6 milliamps of current flowing through the entire circuit from the positive terminal, and the resistor is also allowing 6 milliamps of current to flow, but through each side is 3 milliamps between each parallel resistor here. And that essentially means that sum of each branch of the resistor circuit has to equal the total current in this circuit. Obviously it depends on inductance, capacitance and transistors and things that don't comply to Ohm's law, but that's one of those things that makes Kirchhoff's laws kind of useless outside of the theoretical value that the laws have. So as JHS open source has also asked, an explanation for impedance and reactance is quite simple. Impedance is the same as resistance, but it includes AC sources. So capacitors and inductors also include that, so it's how much current is limited by each of these components that you can see. So basically each resistance is measured in ohms and affects resistors and slightly inductors, but because they work through a magnetic field things are slightly different. Reactance normally just refers to capacitors, and impedance refers to the whole lot as a collective. So to give an example, a real instrument like a multimeter would want a high impedance when it's measuring voltage, because it wants the most accurate reading without drawing a lot of current. So a high impedance in this case is good, or a high resistance. Now what you might find on manuals of multimeter data sheets is they often say an impedance of 10 mega ohms, giga ohms, tera ohms, and as you can tell it's always measured in ohms. That's because it's very closely related to resistance. So let me just have a quick drink. Now then, reactance is normally limited to capacitors. I mean, inductors, yes, it's also relevant. And think of impedance and reactance the same way you think of resistance and conductivity. So resistance is the opposite of conductivity, and impedance is the opposite of reactance. So basically, reactance is how easily something changes voltage or current, whereas impedance is the opposite of that. So if you were building a regulated power supply, so let's say we have our 12 volts RMS AC source, and we put that through a bridge rectifier. Now the 12 volts voltage source could come easily from a transformer, that's absolutely fine, but when it goes through a bridge rectifier it comes out the other side essentially as DC, if not a bit wavy. I'll grab an oscilloscope from the virtual instruments and show you really quickly. Connect one there, and then the other one to ground. Oh, if you have any more questions, anyone watching, then feel free to just comment them, I'll get to them eventually. There we go, add graph. How do I scroll down? Add graph. There we go. And as you should see, if I change the scale of the graph, then all of the voltage is in the positive range. There is no negative voltage shown on the graph, and but it's still quite bumpy. It's not exactly what you'd want for a microcontroller like an Arduino. So that's where capacitors and reactance comes in. So the easiest way to do that, or to demonstrate that, is let's get rid of these wires real quick, is to essentially get some capacitors. I'm just going to use electrolytic, nice and simple ones. We'll get 1 microfarad, and we'll put it across, well, in parallel to the output of the bridge rectifier. Let's see. That was weird about the video game thing. Are you okay? Can you see it now? I don't know what happened there with the whole Kerbal Space Program thing. I just had that in the background in case things got a little quiet. Okay, thank you very much. So how much did I skip out? I can cover back if you want. Or go back over things that I missed and didn't show very well. Anyone? Anyway, I'll just go quickly back over it. Where is it? There it is. Okay, so circuit we've got is 12 volts power source. It can be from a transformer, goes through a bridge rectifier, and essentially in parallel with the output of the bridge rectifier is a capacitor. We'll just get a load real quick, in the form of a resistor, and we'll just put that in parallel. Okay, thanks. I'll work on that. So with the oscilloscope, as you might have been aware, it does leave this rather bumpy graph. But when you add this circuit here, which is essentially a capacitor and a resistor as a load, i.e. whatever you're drawing, it could be, it could be your Arduino, could be a totally different circuit, could be an amplifier for audio purposes, but when you start it up, you can see that it starts to remain at around about the 12 volts mark. Obviously it's a bit spiky, but as you increase the capacitance of this capacitor or add more in parallel, which increases the overall capacitance, that line will actually smooth out. Let's see if we double it. Then yes, the ripple, as it's called, the ripple voltage is essentially halved. Now, that's all well and good. It's all good to have a ripple voltage. As you increase the load, however, let's put it as 100 ohms. You can see that the spikes start to go back down as you're trying to draw a program. Trying to draw current. Goose 183. This is Circuit Wizard. It came free when I joined up with my college, but it's essentially a SPICE program, SPICE. Simulated. I think it's simulated program with emphasis on SPI. Essentially, Circuit Wizard. If you Google SPICE programs, then why does it keep going on to Kerbal? Let's get rid of Kerbal. Go away, Kerbal. Yes. That should be better now. It shouldn't move on its own. It shouldn't have these scene transitions, which is a bit awkward. It should only have Circuit Wizard. Go away. There we go. So, you should have... Yeah, sorry about that. It kept skipping to Kerbal Space Program on its own, but I should have fixed it now. It shouldn't skip anymore. I'm just trying to get used to this program. that I'm using to broadcast, but as you can see it's all a little bit complicated. Now, should be back. Circuit Wizard, let's get that back up. I mean, I had it all set out so you could transition from scene to scene, but it doesn't seem to have worked, so I'm just going to have to roll with just Circuit Wizard for now. But that should be fine, as long as you guys agree. So, where were we? So, as we were saying, reactance is how willing the voltage is to change. It's measured in... Actually, I'm not sure what it's measured in, but essentially what you want for a regulated power supply is as low a reactance as possible and a high impedance as possible, so that once the voltage rises to a certain level it doesn't wobble at all. So let's change this to 100k and I shall show you that it barely moves at all. In fact, it actually keeps going up and down a little bit. I mean, it is very small, but that's the basic principle behind reactance and impedance. Now, what was the next question? How to multiplex and triplex. Unfortunately, I don't do an awful lot of that. Most of that you can do with an Arduino anyway, and I hate to say this, but there's much better videos than anything I can do on the matter. But the basic principle is you turn on a row of you turn on a row of let's see if I can find one in displays. Oh, there we go. You essentially turn on one row at a time of the display. So you see I've got one row and one column, and each of those you can control. Let's get inputs. These are meant for logic, but they work for acting as transistors would, in this case. Copy paste, rotate. Let me just set this up real quick. There we go. Okay, so back to this. As you can see, when you turn on one of the rows, they light up, and when you turn on one of the columns, then every LED in that column would light up too. Now, an example of doing this without multiplexing, and an example of doing the old ways when they struggled before multiplexing came about, is you would have, say you wanted to make a letter I right in the middle, then it's nice and easy. You just turn on one column and all of the rows that you need to make an I shape. But say if you wanted to instead make, let's see, what's an easy enough letter N. So you turn on the two columns on the leftmost side and you put on the LEDs that you want using the rows. Then you want the top one on, so you turn the top one on and you turn on the columns and you end up with a nasty square. Now, the reason why you multiplex is to get rid of all of those unwanted LED flashes that essentially make that big square happen, because multiple LEDs are allowing current to flow when you don't want them to. So multiplexing simply is you turn on one column at a time, and all of the LEDs, or the rows that you need, and then you turn everything off really quickly. Then you turn on the next row, and then do the LEDs that you need on that row, and then the next row, and then the next row, or next column, next column, next column, and then at the other end you do the rest of the ones that you don't need, that you need again, in order to make that N shape, but they just do it really fast so that our eyes can't see it. But if you were to grab a camera, then you would actually see a flickering, very similar to how you do it when you see TV screens, especially cathode ray TV screens, but those ones work on a slightly different principle with cathode rays. But it is essentially column and row scanning, also known as multiplexing. So, Goose, your question was, what type of soldering iron do I have? Let me see if I can get up the listing, because I bought mine I got mine gifted to me for Christmas from Maplins, but it's essentially a variable digital soldering iron. Nothing all that fancy. The tips aren't that fancy either. Soldering iron. I shall show you the page in a second. Main soldering irons. Yeah, it's 60 watts, so it's not all that powerful. It's more than powerful enough to do most jobs, but here we go. Let's see if I can add it on the stream. Let's add a scene. So the screen should have gone black now, but I'm just adding a source real quick. Screen capture, Pro. Go away, Maplins. So as you can see, I should have Maplins up right now. Can you please just let me know, just so that I have got the right screen on. Whoops, I just need to change that. Let's change back to, there we go. So it should be Maplins only, no other tabs should be open. Thank you. It really means a lot to know that the explanations that I've been giving have actually been useful. So yes, I've just brought Maplins up, and this is the exact same soldering iron that I actually use. I will say that I would get, whoops, that's the video, go away video. I would get one of those cotton ball tip cleaners instead of the foam ones, but I do have the replacement tips for it. I mean, you can buy some cheap tips on eBay, but there's no guarantee that they'll fit your soldering iron. But that's what I do. That's what I do use, because I just wanted to be on the safe side. Maybe in the future I'll go and buy some of the cheaper soldering iron tips, and if you want, I can make a video on that too, of the differences between the two. But as far as I know, the Maplin tips, even though they're quite expensive, they have been lasting me for a while. You do only get 3. You get a wedge tip, a very pointy tip, and a less pointy tip. But the wedge tip has lasted me a few months now of on and off soldering at quite a high temperature. I have been running it at 450 degrees, which is the maximum temperature that this soldering iron can go. So what I do with this soldering iron is, because its stand and main body is separate, actually put a small amount of blue tack, white tack, that tacky adhesive thing, and essentially just stuck the holder, the iron holder, on top of the main bit, which, well, saved a bit of space because vertical space isn't used on a desk, whereas the horizontal and depth space is. You can find this exact same soldering iron on a different brand on eBay, a lot cheaper, but I really can't remember what it is. But as far as I'm aware, there are no differences between the two, and I have been enjoying it. I haven't had to replace anything other than the tips. I haven't had to replace the heating element or the thermocouple, which is great because they can be a bit annoying to get to. And as far as I'm aware, it's anti-static free, it's static free, so you have no risk of damaging your components. Yeah, I had a junk one as well, Goose, at first. I mean, it was just one of the ones that you'd plug in for the mains, straight into the mains. There was no temperature adjustment, but it did work. I mean, it was a bit on the clunky side, but eventually I did have to throw it away because I didn't throw it away. I gave it to someone else, but the heating element didn't work as effectively, so it wouldn't melt solder very quickly or very easily. So while we're on the topic of equipment, I'll just go to John Davis's question about, for a budding engineer, what equipment would you suggest that I should buy? So, John, is this for electrical engineering or any of the other types, like mechanical or civil engineering, that kind of thing? Or is it specifically for electrical kind, like the kind that I do? So, just a quick answer for the JHS open source about when and where to use capacitors and inductors. Capacitors tend to be used when you want varying voltage to become more smooth. Typically with switches, you don't want them to bounce as much. You can just put a capacitor in parallel across between the negative or the 0 volts and the bottom of your switch, and it will smooth out any bounce that happens. Obviously it's not perfect, especially when you're using an Arduino, and there are more ways around that by using a 555 timer, but it does the job. As I demonstrated earlier with Circuit Wizard, the using a capacitor to smooth out AC voltages in a power supply is another big one. You can also use it to store large amounts of energy if you have a big capacitor bank at a high voltage, blah 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 blah. But most of the time they're not really used. Capacitors tend to come up a fair bit in electrical circuits, but most of the time they're actually pretty simple in application. But inductors are a bit rarer, really, because they're a bit tricky to use. They're often used in switch mode power supplies, which you can't really design yourself unless you absolutely know what you're doing. I wouldn't either. I wouldn't bother designing one myself. I'd just buy one off eBay. But inductors are the little coil things that you see often on printed circuit boards, and they're normally to limit current, same way as a resistor, but they can also provide a voltage spike. Say if you were to put a lot of current through a resistor, through an inductor, and then suddenly turn it off, the magnetic field around the inductor breaks down and a huge voltage spike is given off. This is known as back EMF, and without proper protection it can destroy your circuits. The same goes with relays and motors because they all have coils in them with a high inductance. So John, back to your question about what equipment should you get for electrical engineering. I would recommend a soldering iron. Let me just quickly go to the Maplins page, because while I'll show you on Maplins, you don't have to go via Maplins. You can go via whatever distributors in your area. You can even just buy cheap I mean, most of the equipment I've got is incredibly cheap, but essentially a soldering iron, any will do. Obviously not something that's ridiculously low wattage. Around about 50 watts here will do. It gets sufficiently hot for you to do your work. You'd also need some solder with that, perhaps some spare tips, but if you're on a budget, then you don't really need it. What else? Well, you need hand tools such as pliers. Do they do pliers? Pliers, snips, and forceps. I would essentially get miniature snip cutters. I use Duron snips. They're about the same price as the ones on eBay, but they leave a very flush surface, especially on PCBs. You can go for the thicker kind like this. You also should get needle nose pliers and very thin needle nose pliers, basically. If you wanted to invest a bit more money, you could go into VDE certified pliers, which are normally insulated to 1000 volts, so if you're working on live equipment, then you won't get a shock. Yes, you can get equipment that is electrostatic discharge proof, so that you don't end up damaging circuits while working on them, but most of the time I found that it doesn't matter. You obviously want a multimeter. You don't need to go ridiculously expensive, especially for your first meter, but I wouldn't go ridiculously cheap either. I mean, this Maplin one, or this analog one, I wouldn't suggest. I mean, this second Maplin multimeter for £20 is reasonably fine. I think I know someone who's got a copy of this myself, or one of these myself, and as long as you know what you're doing, then it should last you for ages. Multimeters typically come with good specs anyway. If you can find an auto-ranging one, i.e. one that has only a few options on the dial and it does the rest itself, then all the better to you. The one I use isn't on here, or at least on this first page. In terms of other equipment, if you had the money, I'd go for an oscilloscope, but oscilloscopes can be a little on the expensive side. I mean, they're more of a luxury than anything, and if you don't really have the money for one, then that's absolutely fine. If there's any equipment you think you need, you can go ahead and buy it. Most of it just comes with experience, but soldering iron, multimeter, and what was the other thing? Pliers and general tools like that. Basically what you need. You don't need anything else really. Move on to another question. Oh yeah, I'll just quickly answer yours, John Davis. Where I learnt this stuff was all college. I mean, I went to college equivalent to high school if you're in America, for 2 years now. I know one of the viewers is actually did attend the same lessons as me. If you're listening, say hi. And most of it I learned through high school, and if you see a book on engineering, you just tend to pick it up if you're enthusiastic about it. I mean, I do that all the time. I buy books for, well, a few quid, equivalent to a few dollars, just pick them up at at second-hand stores. Perhaps never read them, but occasionally you'll find something. I have a few project books by let's see if they're on here. No, they're not on here, but there's essentially a few project books out there which cover the basics, and yeah, shut up, Connor. And give you inspiration. Most of the stuff I learned was out of inspiration. I mean, I do learn a lot from looking at the internet, looking at other YouTubers' projects as well. So just if you're really inspired by electrical engineering, you just tend to pick up things from everywhere and just acquire it all in your brain, and it just stays there. I mean, there's not much else to it. One sec, I just need a drink. So, another question. So I'll do JH Open Source's second about the 5 timer, but for now, let's just cover the capacitor question about what type of capacitors should you use where. Well, typically electrolytic capacitors are normally used in power supplies, since they've got such a high voltage sometimes and quite a high capacitance as well. But they can only really deal with positive voltages, so you can't use them directly on AC, you have to rectify it first, hence why they're most often used in power supplies. But you can get unpolarized electrolytics. They're pretty expensive. They do have higher voltages, but they're normally of lower capacitance values. But they are used in some AC circuits. If you checked out Great Scott's video recently, you can see that inside one of the cases they had a few large capacitors. Let's go for electrolytics, why not? See, the normal radial and the radial capacitors come in a variety of values, and they're the ones you most often see in a lot of circuits, as I said, especially power supplies. Polarized. I'll just put unpolarized in. Hope if I could spell. Let's try that again. Unpolarized capacitors. Yes, so as you can see, where's a good image? Doesn't seem to be one, unfortunately. As you can see, they do look like normal capacitors, but they are, in fact, unpolarized, meaning you can use them in AC circuits without them exploding like you'd expect with a normal capacitor, or with a normal polarized electrolytic capacitor. Where you would use the other types of capacitors, like ceramic, I think it was tantalum bead, something like that. Anyway, any other type other than electrolytic capacitors are normally used for timings and small voltage stabilizations, where perhaps you'd need AC reliability. Say with a filter, you'd normally use an unpolarized capacitor, perhaps an electrolytic, but mostly your other types like ceramic and the others, not electrolytics. I'll just call them unpolarized from now on. Yes, they'd be used in audio filters in order to filter out all the crackles and all of the hums that come with interference. You would use them to stabilize quartz crystals for timings of ICs and timings of ICs. There's not really much other use for a quartz crystal. Like, take your Arduino Nano board. Arduino Uno. Let's just quickly get one up. Arduino Uno. There we go. So if we can get a decent image of the top of the board, you can see that there's a crystal there. I think there's another one on somewhere. Either way, you can see that there's actually a couple of capacitors here on the board. Now they are to stabilize the quartz crystal and get it running at its intended frequency. If you didn't have them, it would be a lot more unstable and your integrated circuit would run a lot more unstably as well. I mean, if you don't have capacitors there, they might not even run at all. So it's an important thing to keep in mind. And moving smoothly on to the 555 timer question of JHS open source, you do use capacitors in there as well. If we get a 555 timer circuit, let's get the monostable. So the monostable circuit here for a 555 timer. Oh look, it's animated. Isn't that nice? I could do this on Circuit Wizard. Yeah, let's do it on Circuit Wizard. Let's get Circuit Wizard back up. Okay, so you should see Circuit Wizard now. If you'd let me know, that'd be great, but I'll just hope that my software's worked this time. But yes, 555 timer is up. I'm not going to bother about power so much, and we'll just copy the circuit diagram here. And another one there. Let me just find my images reference. Basically, each pin of a 555 timer does a separate job. Most of the time, you'd only use a 555 timer for either monostable or astable circuitry. Astable meaning it creates a series of pulses that goes on at a specific frequency, in which the capacitor C1 is used to select the frequency along with resistors R1 and R2. The different capacitance and resistant values determine the frequency at which it runs. I would suggest using, I think it's House of Jeff's 555 calculator. A stable calculation. House of Jeff, yes. Because this one, from my experience, seems to be the best. I wouldn't bother with working out the maths behind it yourself. But this is the astable circuit, the one that outputs a certain frequency, and you literally just put in the frequency that you want. That is a big value, but it's perfectly within the range of a capacitor or of a 555 timer, and you will come up with a small table with the exact values that you need, plus or minus a few hertz and plus or minus a bit on duty cycle as well, so you can just choose the values, plug them in, and off you go. It's nice and handy that he gave a little circuit there. As for the monostable mode, there is also other calculators out there. I don't think House of Jeff does the monostable mode, but essentially the way the monostable mode works is you have a switch connected to the trigger. Is that on the trigger? One of these is trigger. Yes, the trigger pin, and when that gets pulled below a certain voltage, the IC triggers and the voltage goes high for a certain amount of time, dictated by capacitor 1 and resistor 1 as well, if you're using R2 as a pull-up resistor for the switch, as we saw in this example. I mean, it's a bit bad because they switched around R1 and R2, but so be it. Let's see. Let's question going. So I did that one, did that one. What would you say is the coolest thing you have ever built is? Well, I am pretty impressed with the wire cutter that I did not too long ago, as you might be aware. Let's just quickly go on my YouTube video, my YouTube channel. Yeah, we're on my channel, and not my other channel, which is for my own personal usage. So let's just, I'm not going to play the video because it's a bit long, but the one that I most enjoyed was, oh, it's not on here. I must have uploaded it. Anyway, I basically made a foam cutter board for prop making, and it can essentially cut polystyrene, your foam boards, that kind of thing, and it's not the coolest as in you can show it off to your friends because it's not one of them, but I actually found it the most impressive because it's just awesome to be able to say that you've made this yourself and you can do things with it, and it's just one of the most epic things to know that something you made actually works. I mean, I get that feeling a lot with everything else that I do, but so be it. I mean, it's just great to make something and have it work, to be honest with you. I mean, not everything works. The first project that I ever did, or attempted, was a 24-hour clock made out of individual logic circuitry, or individual logic chips. That absolutely failed when I tried to do it in real life. I made it on Circuit Wizard and it worked fine. I don't think I have one. Oh, I might still... Nope. I thought I had the save file, but I don't. So yes, when it works, it's a great feeling. I'd say it's the coolest thing ever. I mean, but when it doesn't work, it's the most infuriating thing ever, but you just have to deal with it. I just noticed your newest question, John. But in terms of the actual coolest thing I've ever made, not a lot. I made a line following robot out of Lego. It didn't really move very fast, so I wouldn't say that's all that cool. I do have a project in the works, but unfortunately the Arduino Nano that I was using blew up on me. I accidentally applied 12 volts to the 5 volt output and the regulator just went poof, but that was just due to a stray wire there. And yeah, that's it. So, yes, your latest question, John. Was everyone at this college as good as you at engineering, or was it just you in a room full of idiots? Yeah, that is pretty good, Goose. I do like that as well. Or was it just you in a room full of idiots pulling them along to finish the course? That's exactly the wording that a friend of mine would say, who isn't actually watching this, or as far as I'm aware isn't watching this. I mean, he could have created an account called John Davis and joined in, but but yeah, it was essentially a room full of idiots, including Connor, who I don't know whether is still here or not. And yes, I was pulling them along at the end, I will say that. I was so proud when I made my first. Yeah, I do like that. Thank you, Connor. Thank you. first Arduino circuits I also made was a dimming slash pulsing LED circuit as well. I mean, circuit wizards can't do Arduinos, unfortunately, which means I can't show you, but yeah, it is pretty fun to do, so I certainly do enjoy making them. I actually have a video somewhere, not on my channel, but on my phone of just a red, green, blue LED pulsing on a certain blue colour. It is very creative. Does anyone else have any questions for me, or can you not think of anything? Yes, I do have some videos coming up, or should do, but I have no but I won't be having a lot of time, unfortunately. I'm starting work soon on the 5th, which is a bit of a shame, but so be it. I'll still try and make videos as often as I can, maybe about the same frequencies I do now. Thank you, Connor, for that fabulous comment or question. And to be honest with you, I don't know, so I'm going to Google that. I know it's a reference to Monty Python, but I don't care. It's a shame Google didn't give me a direct answer there. Oh well. Ah, right, that's what I mean. Oh, that's what you mean, Goose, about the pulsing LED circuit. Yeah, I mean, I know what you mean about the whole doing it using a 5 for 5 to make a pulsing LED, but it is an awful lot easier to do it on an Arduino, because it's simply just write code in which the pulse width modulation goes up, and then back down, and then back up, and then back down. I mean, you do have to bear in mind that pulse width modulation is logarithmic to our eyes, i.e. it starts off accelerating really quickly, but then the brightness after around about, I think it's around about 100 out of 255. Anything above 100 doesn't really change pulse width modulation wise. Thank you very much, JHS Open Source. You can feel free to ask me any other questions if you'd like. Same with the rest of you. And yeah, it's just one of those things where Arduinos replace everything, really. Like, you can learn about 4000 series ICs or 7400 series ICs and use them, and they're still very, very helpful. But they're being replaced so much by Arduinos, which is a good thing. I mean, it is a good thing, but you lose a bit of knowledge by not learning about the series ICs and how they work. Like on one of Great Scott's videos recently with the coil gun, he started with an Arduino and didn't explain much of the code because most of it was self-explanatory. Most of the circuitry was self-explanatory. But when he went on to building it out of discrete components, he had to explain an awful lot about each component and how they work. I mean, that is how 4000 series or 7400 series ICs worked. Like, yeah, but it's just you lose something. I mean, if you start off with Arduino, go back and learn 4000 series ICs and how logic gates work, then all the more to you. I mean, you see a lot of people asking questions about how do I get or two or more inputs to essentially turn into one input without using the Arduino itself. So the easiest way would be with a diode, but when you're working on 3.3 volts logic, that can be a bit iffy, because it falls into a grey zone between logic high and logic low, and it doesn't have a clear 0 volts or 3.3 volts in this case. But you could use a tri-state buffer which allows for the input to be pulled high, low, or pulled high by another input. Essentially, if you have several tri-state buffers in parallel, essentially just connected up to each other, then one of them can pull the rest high without affecting any circuitry. Whereas if you try to do that with normal logic gates or diodes, it doesn't quite work. So sometimes diodes and things would work, sometimes they wouldn't. So the more knowledge you have, the better there is. Better prepared you are for these kind of challenges that you face in the engineering field. But it's just one of them. The more you know, the more you can apply it. Out of interest, do they still teach about the old ICs in college? Yes, they do, but I think they're fading out a lot. The college I went to, yes, they do still teach about them. They do still teach about the 7400 IC series at least. 4000 series 4000 series ICs, not so much, but the differences between the two are negligible. You can do a bit of a comparison on some courseworks and independent study, and you will get there eventually. Sorry about leaving the screen just on 5 timer calculator, but they do still teach old ICs. They teach newer things as well, but not so much. They still use microchip branded microcontrollers instead of Arduino, which is in my opinion, it's the easier one to program for. But with microchip and the MPASM language that they use, you do get control of each individual, essentially, pulse of the frequency. But yes, it's easier. It's usually a bit better to not copy a script, but to build everything yourself from the ground up. But copying a script is a great way to get into it at the start. I mean, when I started learning Arduino after finishing college, not too long ago, I did start with some example scripts and some simple LEDs, and essentially change the scripts in order to meet the one that I was what was I saying? I forgot now. I've totally forgot. I got distracted by JH Open Source's comment about the 7400 series ICs. But yeah, you're absolutely right. Digital electronics courses do teach that about the 7400 series. But yeah, it's not all that popular, and it's one of those. You just have to have the determination, or else you'll end up dropping it. But if you do finish, you'll be in good standing for a career in engineering, and perhaps become a pro at this. So I'm getting pretty tired. It's almost 11:30 my time, and yeah, that's true. You don't need to reinvent the wheel every time. And I'll take one round of questions from everybody. If you have any left before I go. But if you have multiple questions, feel free to ask them. I mean, I'm not going to take one from each of you. If there's several questions that you want to ask, I'll happily answer 2 or 3 before I go. But yeah, just go ahead and ask them. If no one has any, then that's fine by me. I'll leave it a week. If you have any more, then you can contact me via Twitter or on a comment on my other YouTube videos, and perhaps in another live stream. You guys seem to have liked it, so I'm more than happy to try and stream again. I might do one before I start work, but might not have time. I might do one after. I'm absolutely fine with doing one about the same time after school as well. After work as well. After school. I'm so used to being in education, and I've only just finished. Yeah, I will do another live stream eventually. But as I said, it's up to work and time that I have available. My Twitter is at TechNewEngineer. Let's see if I can get it up on screen. One second. So it's just gone black screen. I'll just get that back up. Window capture. There we go. This is my Twitter account at TechNewEngineer down here. And yeah, if you want to ask me questions, then feel free to leave them here. But if not, then fine. I'm absolutely fine with that. If you want to ask me on Facebook, I am fine with that too. Did I say Facebook? I don't even have Facebook. If you want to ask me on the comment section, then that is absolutely fine. And I'll have more videos coming soon, hopefully with one of the cool videos that I teased at in a couple of my tweets. But yes, I think it's about time that I say goodbye to you guys. Thank you ever so much for watching. If you want to check out my other videos, then I'm absolutely fine with that. You can tell that my voice is starting to go. I'm not used to talking for an hour and 6.5 minutes straight. And yes, thank you. Thank you, JH Open Source, for the Twitter name. It might be around the same time, so if you're available and like this time, then you go ahead and join in if that's what you want. I will do some other times in case some people in other countries, like the UK. Okay. Go away. Yes, good night everybody. I'll see you all soon.